Welcome back to The Explainer. So today, we're wrapping up our deep dive into secondary barrier design and ship types. This is basically the ultimate conclusion to how we engineer our way out of catastrophic gas leaks.
Just to quickly set the stage, in Part 1 we talked about physically keeping the tank in place, right? We looked at how cradles and keyways manage that massive thermal shrinkage and how anti-float brackets prevent flooding hazards. Okay, so we've got the primary tank secured, but now we have to ask the big question. What actually happens in that space between the tank and the hull if the primary tank fails anyway?
Okay, let's dive into this. That gap between the cargo tank and the ship's hull structure, it's called the hold space, and it's definitely not just empty air. It is actively monitored. It's usually filled with either inert gas or dry air, so inert gas for flammable cargo or dry air if you're hauling ammonia. And the whole reason we do this is specifically so your gas detectors can catch the absolute earliest possible trace of a leak way before it becomes a visible or dangerous problem anywhere else. Honestly, if you're ever doing commissioning checks, calibrating the gas detection in this hold space is one of your absolute highest value tasks, because this is your very first warning line.
And it's not just sitting there passively either. The hold space is an active defense layer. It requires its own dedicated, independent build system to pump out any cargo leaks or even just condensed water. This has to be completely separated from your standard machinery drain system. Whether you're using ejectors or deep well pumps, this setup ensures that if something does leak, it doesn't just pull up and destroy the thermal integrity of the surrounding structure.
But, all right, let's say the absolute worst happens. A leak occurs, and it hits your secondary barrier. The moment that liquid hits, a ticking clock starts, and it revolves around a very specific, incredibly critical number, 15. Whether your secondary barrier is a full backup tank on a Type A design or a really sophisticated drip tray on a Type B, it legally has to be capable of containing a primary leak for exactly 15 days.
Which brings me to a quick check for you. This 15-day containment standard, what real-world constraint is that actually based on? I mean, do you think a committee just sat around and pulled a nice round number out of thin air to make a safety margin? No way. It is a brutally practical operational figure. 15 days is a realistic estimate of exactly how long it takes a massive, fully loaded gas carrier to safely divert across the ocean to a suitable repair port after a leak is detected. It ensures the leak is contained without exceeding what the hold structure and the insulation can tolerate during that transit time. So it's not just a bureaucratic guess. It's literal maritime isolation translated directly into structural engineering. And what's really interesting about this comparison is how it shows exactly what happens to different materials during a leak. If a cryogenic liquid hits ordinary mild steel, it instantly becomes brittle and can fracture suddenly, literally shattering like glass. That is exactly why the hold structure adjacent to these low-temp tanks has to use specially rated steel. It must be engineered to survive the absolute worst-case, lowest temperature that structure could realistically be exposed to during a leak. Not just the normal operating temperature, the leak temperature. Skimping on the steel grade here to save a few bucks is a classic, catastrophic design failure, and preventing it is exactly why the IGC Code's temperature rules exist in the first place.
So, moving on to ship hazard types and clearance rules. We've figured out the micro-containment story inside the hull, but now the IGC Code zooms out to classify the entire ship based purely on the danger level of the cargo itself.
The philosophy here is broken down to 4 operating classifications. Let's look at the worst case first. For hyperhazardous cargoes, like chlorine, the ship is a Type 1G. Because a chlorine release is so toxic, there's basically zero acceptable margin for error in a collision. So those tanks have to sit the absolute furthest inboard, at least a fifth of the ship's beam, up to 11.5 meters away from the side shell. Then you have severe, but slightly less catastrophic hazards, like LNG and ammonia. Those are Types 2G and 2PG, which require moderate clearance. And finally, the lowest hazard tier is Type 3G, for things like LPG, meaning those tanks can safely sit closer to the outer shell.
It really just boils down to one unbreakable physical rule. The higher the hazard, the farther the tanks sit from the outer shell. That single rule dictates the entire physical architecture of the ship. It's a perfect example of how the chemistry of the cargo literally dictates the structural flexibility of the vessel.
Now, speaking of structural flexibility, let's quickly touch on carrier operating classes. Beyond the hazard type, how does the ship actually manage the immense pressure and temperature of these gases?
Well, Every gas carrier fits into one of three classes. First up, fully pressurized. These use thick-walled Type C tanks at ambient temperatures. They handle high pressures, up to 17 or 18 bar, so they need absolutely zero refrigeration plant. They're simple, they're cheap, but they are incredibly heavy. Next is the middle ground, semi-pressurized carriers. They use Type C tanks with partial refrigeration, dropping the pressure to a highly flexible 5 to 11 bar. And lastly, fully refrigerated carriers. These use large, insulated Type A or B tanks running at near atmospheric pressure, so under 0.7 bar. So the crucial point is this: choosing the wrong pressure class isn't just a technical oversight, it's a massive commercial mistake that dictates the ship's cost and capability for its entire lifespan.
Actually, let's do one more quick knowledge check to make sure we're connecting the tank types with their thermal requirements. Out of those three carrier classes, which one requires a full on-board refrigeration plant to keep the cargo near its boiling point at low pressure?
Yep, it's the fully refrigerated carriers. For cargoes like LNG, carried at a blistering minus 163 degrees Celsius, the refrigeration plant, or the clever use of boil-off gas for ship propulsion, constantly removes the heat leaking into the tank. Basically, the plant does all the heavy lifting, which effectively replaces the need for those super thick, incredibly heavy, and expensive pressure vessel walls.
Put it all together, and it brilliantly illustrates this complete fail-safe cascade we've been walking through today. The hold space immediately warns you of a leak. The secondary barrier catches it and buys you 15 days of transit time. The rated steel ensures the hull doesn't fracture from the extreme cold during those 15 days. And overarching the whole shebang, the ship type classification ensures that if there's a collision in the first place, your most dangerous cargoes are buried so deeply inside the hull that they stay protected. It's a completely unbroken chain of structural protection for both the crew and the ocean.
But I want to leave you with a truly chilling thought for next time. We've engineered the tanks, the steel, and the hull clearance to perfectly contain the physical pressure and temperature of a leak. But what happens when the threat isn't physical at all? What happens when a reactive cargo like butadiene or VCM starts a chemical chain reaction, like polymerization, mid-voyage, and starts generating its own massive heat from the inside out? Well, you're going to want to think about those inhibitor certificates and expiry dates, because in our next explainer, we are diving deep into the fascinating chemistry of reactive cargoes. You definitely won't want to miss it.